Hello and welcome to my video on the Work Energy Theorem and conservation of energy. So kind of pushing two thoughts in one here because they are tightly integrated. The Work Energy Theorem is basically one that tells us that the work is equal to the oftentimes the heat energy or the wasted energy in a situation. Which would also be described as the change in energy. Also, as we know, sometimes force times distance. But the change in energy, we're not going to talk about the force times distance that much in this video. But the change in energy is the energy final minus the energy initial. And so we're talking about a specific type of energy. So we know because of conservation of energy that there actually is no change from beginning to end if energy is conserved, and energy is always conserved if you include all types of energy. But oftentimes we just talk about the mechanical energy. So mechanical energy final minus the mechanical energy initial. And so that would be kinetic and potential energies combined. And so the most common form of wasted heat or heat loss or wasted energy or in this case friction would be type of friction, so often heat loss, and so we call it delta H. It could also be light or sound as well, as you can sometimes hear scraping sound when something's rubbing against the floor, or squeaking sound. Those would be causes of energy loss as well. Okay, so here are two quick examples for this in terms of the work energy theorem, and I believe the next video is going to be a little bit more about conservation of energy. But let's take a look at these two examples. We might add one more at the end here if these aren't long enough. And actually, let me just give a little bit more space. Okay, so smart cars are extremely small, light, fuel-efficient, 3-cylinder cars. Tiny, tiny engines. Determine the amount of work that needs to be done to accelerate a smart car from that to that, so from 10 meters per second to 30 meters per second. Okay, so if that's the weight of a smart car, how much energy is required to accelerate a car from there to there? Or how much work needs to be done? Well, it's the change in energy. So work equals the change in energy. So the energy final minus the energy initial. Well, in this case, the final is going to be based entirely on the kinetic energy. And same with the initial. It's based entirely on kinetic energy. Okay, so if we were to explain those a little bit further, we'd write mvf squared over 2 plus mvi squared over 2. If we wanted to, we could also write it like this: m over 2 vf squared minus vi squared, and we could leave it there if we wanted to. So that is pretty much it. Let's start putting in some of these values here. 790 kilograms over 2. And then our final velocity is 30 squared. Our initial is 10 squared. And this is in meters per second. Okay, so let's go ahead and try this out. $30 minus 10, 20. So our energy usage here is 7,900 joules, and so that would be 7.9 kilojoules of energy. Yeah, we only have 2 sig digs, so that would be where we should leave that. All right, taking a look at the second one here. It is a similar type of situation. Again, this is more work energy theorem, conservation of energy. I think there'll be some examples in the next video. So take a look at that as well. A 165-gram hockey puck is sliding at 20 meters per second, slows down to 9 meters per second in a distance of 8.1 meters. Determine the force of friction causing the puck to slow. Well, there's a little bit to think about here. Basically, if you think about the over the course of 8.1 meters, this is the distance. You could solve this a few different ways. We could find the acceleration, right? And we know force, so in this case force of friction equals mass times acceleration. If there's no other forces acting on it, then so F net equals ma, and ma equals the only force acting on it, which is Ff. So if it goes that distance and Vi is 20, Vf is 9, we can actually solve for acceleration here. So it's Vf squared equals Vi squared plus 2AD. Okay, solving for A, that's Vf squared minus Vi squared equals 2AD. Okay, one more time, Vf squared minus Vi squared over 2D equals A. So plugging all of that in, that's 20 squared minus 9 squared over 2 times 8.1. Let's try this out. 20 squared minus 9 squared over 2 times 8.1. This gives us the acceleration of the hockey puck. And obviously it's deaccelerating with this. But yeah, there we have it. So if we are looking for the force of friction, then this is actually going to be just times by ma. So or equals ma, which is mass, which is 165 grams. Actually, that would be 0.165 kilograms times by the acceleration due to friction, which is actually quite a bit, quite a deacceleration. I wonder if that's realistic. I don't know. 0.86. Okay, and so this tells us the force of friction equals 3.249 newtons. And we've got 2 sig digs, so 3.2 newtons. Alright, so that's our answer for part A. Determine the efficiency of the system if the goal is to slide for as long as possible. So basically, how much wasted energy was there? Well, what we need to do is for efficiency, we need to basically take the energy final divided by energy initial times by 100% in order to find the efficiency. Basically, how much energy loss? Actually, energy final minus energy initial. What's the change in energy over the total original energy? Maybe I'll write it like this. Delta E, the change in energy. So if we were to try to write this down, energy final is going to be mvf squared over 2. Energy initial, mvi squared over 2. And then mvi squared over 2 is going to be at the bottom here. We can probably do a little bit of flipping and canceling. So yeah, we can cancel out the masses and dividing by 2 everywhere. So that's nice. So it's Vf squared minus Vi squared over Vi squared. So let's just plug that in the calculator. I guess let's write it out one more time. So 20 squared minus 9 squared. Nope, other way around. 9 squared minus 20 squared over 20 squared. And obviously that'll get a negative answer, but that's, I guess, not really ideal. So flip that around. So 20 yeah, I guess I had that flipped around. So anyways, it would be, and then times by 100. That I forgot to write. So that would be 79.75%. So with sig digs, 80% efficiency. That's actually not too bad. I guess tells you that the sliding on ice has some benefits. All right, so hopefully this video helped you understand efficiency and the work energy theorem. I guess conservation of energy, we'll talk a little bit more about it in the next video. We just briefly mentioned it here, but I hope this video helped, and good luck.